Welcome back, everyone. Today we're working on Newton's second law of motion, also referred to with the equation F equals ma. And we'll go over that just briefly right at the beginning. I know we don't like to dive into equations too much into these videos. I like to more talk about what's going on and conceptually how things are moving and changing, but math is how it all works. And so briefly, there's a little bit of calculus here that talks about the derivatives with respect to time of momentum. Now, momentum is given by this fancy little p here, and let's just remember it equals mass times velocity. And so if we take our derivative with respect to time of momentum, we're left with this over here. We're left with simply mass times acceleration. And we can walk through this in depth in another video in the future. But it is only if the mass of our object stays constant. Right? If it burns all up, then all right, like we're talking about something else, we're talking about chemical changes, losing mass, and everything will be different. But as long as your mass stays constant, this will hold true that your force, net, is equal to your mass times acceleration. And net simply means, let's just say we have an object right here, and there's a force coming this way, and there's also a force coming this way. Those two will cancel each other out. But if one of them was a lot stronger, and will indicate stronger by a longer arrow than a weaker one, guess what direction this object is going to end up moving? Yep, it's going to end up moving F net in this direction. Even though there is still a little force here, this one is more powerful or stronger or larger. Therefore, there will be a net motion move in that direction. Okay. Now, what is this thing about momentum? I know we talk a lot about momentum when it comes to sports. And for example, in the World Cup this last summer, there's a lot of games where momentum changed, right? A team's behind, all of a sudden they score a goal. It's like they got a new energy, like we're in this still, and the whole mood changes, and then they come back and win the game. And I like to think that Messi right here would be the king of the change in momentum. He's always there to bring back the energy and bring back the fire inside of his team. And real quick, we'll just define force again. Our force is equal to the change in momentum of an object with respect to the change in time. And this equals our net force applied on that object. And so think about our objects as a game, like a soccer game. If you hit it with a force, it's going to cause it to move. Change the energy. Change the way it's moving, either its speed or its direction. Now, something that absolutely doesn't want anything to move is how much mass is in that object. The definition of mass is the substance of an object that resists a change in motion or velocity. Now, last video we talked about which would be harder to move, a Tundra or a shopping cart in a grocery store. And we're ready for the answer, and it is the Tundra, a lot easier to move. Just kidding, just kidding. You probably thought anything you've learned about this world is wrong. No. Of course, the Tundra is harder to move, and that's because the heavier object digs into the ground more, causing more friction to oppose your motion. You want to push this way? Because of all of this weight, 5,000 kilograms, it's driving a crazy hard friction force that way. It opposes your motion. Okay. Also, simply the fact that it is this large will resist acceleration, and you will have to create a lot larger force this way to be able to overcome this resistance to motion, resistance to acceleration. And comparing to a shopping cart, you'll have to have just a tiny little force to be able to overcome the friction that will come from the small force downward, also from the fact that this weighs 20 kilograms, therefore resists acceleration a tiny bit, but nothing near compared to what our tundra does. Okay, acceleration, the other part of F equals ma. Acceleration defines how an object is changing motion. And that motion can be changed either by the speed or the direction. Here, we've got a rocket pushing off of the moon, and it starts at 0, goes to 1,000. And since our acceleration equals the change in velocity over change in time, we can do that right here. And since we started at 0, went to 1,000, change in velocity is 1,000 over time. This was over 2 seconds. So 1,000 divided by 2 is 500 meters per second squared. That's our acceleration. Now, an acceleration doesn't have to always come from a change in velocity. We could be in this car right here, moving forwards, and we could simply be moving at 10 miles per hour and not put on the brakes at all. But what happens if you don't slow down at a turn? Well, what happens is you find yourself being pushed to this side of the car. But if we're not changing our speed, it's because we're changing our direction. We were going this way, now we're going this way. And there is still a force at play, still an acceleration at play. And we'll get to more of that when we talk about circular motion in a future video. Now, to wrap up with the definition on what a force is a push or pull on an object, which can change the object's direction or velocity, if and only if there is not another force to cancel out the original force. This is why we don't say, in a more complete definition, F equals ma, we say F net. Just like we talked about earlier at the top, if there's an object and there's multiple forces, we have to figure out what direction it ends up moving, and that net force, or the one that outcompetes the others, will be the one that equals the mass times acceleration. Now, next video, we'll be talking about Newton's third law of motion, and then moving on into, okay, so why do we even care about these laws of motion? And we'll get into all the applications. But thank you so much for watching.